Stand on a Manhattan sidewalk, and the city convinces you it's permanent. Steel cliffs, stone canyons, towers that seem hammered into the bedrock. But that stillness is a carefully maintained lie. High above your head, where the air thins and the wind sharpens, New York's skyscrapers are moving. Not dramatically, not visibly, but constantly. They lean, they recover, they sway. And the unsettling truth is this: if they didn't move, many of them would fail. This isn't a design flaw. It's the very reason the city can rise at all. This is the story of how New York City learned that survival in the sky depends not on stiffness, but on controlled flexibility. New York's real adversary is invisible and relentless: wind. At street level, it's just background noise. But above 200 meters, wind becomes a structural event. It accelerates, collides, and strikes buildings with sustained force. Unlike an earthquake, the wind keeps coming. Every gust bends a skyscraper slightly, building energy into the structure. Early engineers thought the solution was obvious: make buildings heavier, stiffer, more rigid. That assumption nearly capped the city's vertical ambitions. At the start of the 20th century, New York was obsessed with height. Steel frames made it possible, elevators made it practical, and land prices made it necessary. But as towers rose higher, something strange began to happen. Buildings that were structurally sound just felt wrong. Office workers complained of dizziness. Papers slid across desks. Chandeliers swayed on upper floors. Engineers eventually realized the issue wasn't weakness, it was stiffness. A rigid structure absorbs energy poorly. Stress concentrates at its joints. The solution was counterintuitive. Tall buildings must be allowed to move. This realization reshaped skyscraper design worldwide. Steel frames were no longer seen as immovable skeletons. They became elastic systems. Engineers began calculating acceptable motion, focusing not just on survival, but on habitability. A modern skyscraper may sway several centimeters in moderate wind and half a meter or more during extreme storms. You don't see it from the street, but your inner ear might notice it inside. And that motion is precisely what keeps the structure safe. When the Empire State Building opened in 1931, it was an experiment. Built with incredible speed, it revealed how steel-framed buildings behave under wind stress. Engineers discovered its slight flexibility allowed it to absorb gusts without cracking. Over the decades, it endured storms and hurricanes not by accident, but because it bent, returned, and endured. The Empire State quietly taught New York a lesson it would never forget. Height without flexibility is a dead end. As technology improved, skyscrapers became thinner, taller, more daring. This created a new problem. A slender building moves and twists more, amplifying wind forces. Enter the era of extreme engineering. Towers like 432 Park Avenue pushed height-to-width ratios to unprecedented extremes. These slender giants needed help, and that help came in the form of massive internal systems designed to fight motion with motion. Hidden near the tops of many modern skyscrapers are machines most occupants never see: tuned mass dampers. They are enormous weights, sometimes hundreds of tons, suspended and precisely calibrated. When wind pushes the building in one direction, the damper moves in the opposite direction. This motion cancels out part of the sway, reducing both structural stress and human discomfort. It's not brute force. It's choreography. A building sways, the damper answers, and the system finds balance. After 2001, skyscraper design in New York entered a new phase, focusing on redundancy, resilience, and recovery. One World Trade Center embodies this philosophy. Its reinforced concrete core provides extraordinary strength, while its steel perimeter allows controlled movement. Its very shape is designed to reduce wind vortex effects that can cause violent oscillations. A building doesn't resist nature aggressively. It anticipates it. Flexibility became not just an engineering choice, but a symbol of endurance. The fact that most people don't know their building is moving is intentional. Human comfort thresholds are carefully studied. Engineers know exactly how much motion people can tolerate before anxiety sets in. That's why the sway is slow, gentle, almost imperceptible. The movement takes seconds, not moments, avoiding the feeling that triggers panic. New York's skyline is engineered not just for physics, but for psychology. The city understands that trust is as important as steel. Myths about skyscrapers refuse to die. People still believe they should be rigid, that movement means failure, that older buildings were built stronger. The truth is quieter and more elegant. Strength today is measured by adaptability. Safety is measured by how well a structure yields under pressure. New York's tallest buildings are not defying nature. They are negotiating with it. Seen from a distance, Manhattan looks fixed. But conceptually, the illusion breaks. Every tower responds to wind differently, each with its own rhythm. The skyline is never perfectly still. New York breathes vertically. It expands in heat, contracts in cold, leans in storms, and straightens afterward. This constant motion is not chaos. It is balance. The next time you walk beneath New York's skyscrapers, remember this. They are not frozen monuments. They are living systems, engineered compromises between ambition and reality. They sway so they can stand. They bend so they don't break. They move so the city can endure. And somewhere far above the noise, steel and wind are locked in a silent conversation that never ends. Thanks for watching. Follow us for more stories about the engineering that shapes our world.